3.5, we're going to finish up this section talking about division of whole numbers. And we had left off at the point where we're going to talk about some division algorithms. And there are only two division algorithms that we have that we're going to work through. One of them is the standard algorithm that you know and know well. And then the other one is called partial quotients, or sometimes you'll hear it called repeated subtraction. So that's another title that it's given in different resources. So as you know, with the standard algorithm, we will write this like so. And we ask ourselves something like this. And it works fine when it's a single digit. It's when there's multiple digits that students get a little bit more sketchy on, because when I'm dividing by 5, hopefully your kids at the point when they're learning division, and I say hopefully because it's just not always true. Hopefully they know some of their multiplication tables. Hopefully they know them all. And so the division will rely heavily back upon their ability to do their multiplication facts. So when I look at 5 and I say how many times does 5 go into 6, the answer would be 1 time, and we'd write the 1 down here, and 1 times 5 is 5. So I subtract, and then I bring the 2 down. So now I have 12. 5 goes into 12 2 times. So I write the 2 above the 2 where the 12 was. I multiply and subtract, and I get a 2, and then I bring my 3 down. And then 5 goes into 23 4 times. Sometimes things work out nicely. On this one, they end up not working out so nicely. That is to say, I get a remainder. So at a very early age, and for what we're working on for this level of content, we're writing our answer as 124 remainder 3. So like I said, the standard algorithm is probably going to be your go-to one because you know it, obviously. It also works really nicely if you know your multiplication tables, right? Have those memorized, and we would hope that most of our students would be there. But I have a 7th grade daughter who struggles with multiplication tables. And no joke, we've memorized it. Like, I have sat down and memorized it with her twice, and she memorized it with her previous place where she was before she lived with me before that. So she has flat out memorized these things 3 times, and they don't stick. And I don't have a good solution as to why. I really don't know. So I do know that sometimes these things are hard for our kids in our schools because those memorization facts, whether for legit reasons or not, are not stuck the way that they should be. The other thing that comes into play is that you only memorize multiplication tables up to a certain point. So these days, it usually goes up to 12s. I don't know why 12 is the magic number. I mean, why don't we stop at 10 like we did back when I was a child? I have no idea why. But people want to memorize, but they don't go any higher than 12s usually. So if you're doing this same problem, but instead of it saying 623 divided by 5, it said 623 divided by 17, this is a much more difficult question because I don't have multiplication tables of 17s in my head, even if I have good multiplication tables of other things. I don't do 17s. So when we do this, just as an example, it becomes a more difficult question, right? Because now I've got to figure out how many times does 17 go into 6? Well, that doesn't happen. Well, how many times does it go into 62? So what you see kids doing a lot of times is either skip counting, or they'll grab a scratch piece of paper and they'll try things at random. And so it's a tedious problem. It's really not straightforward. It's not easy. And so one of the things that I tell my kids to do usually is to say, okay, well, 17 is pretty close to 20. Okay, so they're using an estimation technique to do it. And they'll say, how many times does 20 go into 62? Right? That's an easier question. I can do that quickly in my head, maybe at least quicker than 17s. And so there's some nuances to that make this harder when it's not a single digit division. So as I'm saying that, that's probably the best reason why there's another algorithm that I'm going to show you, is because it's not always easy for a variety of reasons. So this is called partial quotients. You're going to hear me call it repeated subtraction because that's what our book called it for years before it changed the name, and so some books will call it that. So it works much the same way in the sense of how it's set up. Okay? So what you're thinking about instead, though, is the fact that this is the number 6 as in 600. Okay? So what we're going to be doing is we're going to be multiplying and subtracting things that have 5 times a power of 10. So 5 times 100 would be 500. Okay, so I'm subtracting from, I'm thinking more about really like place value when I'm doing this, right? 623 minus 500. We're not writing anything on top of it, by the way. We'll come back to the answer part in a minute. This gives me 123. Now, if I could subtract 500 again, that's what I would do. I can't here. I only have 123, so I'm not going to subtract 500. So the next thing I'm going to do is I'm going to subtract a 5 with a different power of 10, right? So I'm subtracting things like 5,000, 500, 50, and 5. All the things that are easy to multiply 5 by. We'll do it with the 17 in a moment so you can see why it's helpful in that sense, whereas maybe here you're like, this seems silly. Bear with me, I promise, okay? So we're going to subtract 50, and again, that's because it's 5 times 10. So 123 minus 50 would be 73, and I mentioned it before. If I could have subtracted 500 again, I would have. Well, if I can subtract 50 again here, I will, and I can, right? 50 will still take away from 73 just fine, so it's another 5 times 10. I'm sort of keeping track over here. At the very least, you need to keep track of what you've been multiplying the 5 by each time, because that's going to be part of our answer in a moment. So 73 minus 50 would be 23. Can I subtract 50 again? No, I cannot. So I'm going to shift this up because I'm running out of space. So I can't subtract 50 again, so I'm going to subtract now 5 times 1, which is just 5s. So I'm going to keep subtracting 5s until I'm done. So you're always subtracting the number you're multiplying by, or dividing by, excuse me, times the power of 10. 23 minus 5 would be 18. Can I subtract 5 again? I need to keep track of them, so I'm going to keep writing them to the side. 18 minus 5. Okay, subtract 5 again. What's 13 minus 5? 8. I'm running out of space. I'm just going to start a new column. 8. And then 8 minus 5 one more time would be 3. So I can't do it again. I've exhausted all my ability to subtract multiples of the divisor. And the solution is in these times powers of 10. So in other words, I've got 100, 10, 20, that's 120, 1, 2, 3, 4, 124 with a remainder of 3. Admittedly, it feels unnecessary for division by 5. So let's run through it with division by 17 just so you can see how it's a little more helpful when it's a less common divisor that we're working with. And I don't have this written down or anything, so I have no idea what's going to happen. I made it up. So we always subtract 17 times a power of 10. Well, I can't do 17 times 100 because I don't have a number that big, but I can do 17 times 10, which would be 170, right? I can subtract 170. That's fine. So we'll subtract. We get 3, 12, so it's 5, and then 4. 453, I think. I did that really quick. Y'all can check me as we go. And we would do it again. 17 times 10. Okay, so that's another 170. There's the 3. 8 and 2. Does that look okay? And then we're going to do 170 again because it still can. We're going to keep doing the subtraction with the 170. So now we've done it 10, 20, 30 times. That's what we've really done is we've multiplied. This is a 30 at this point. So we have 3, 1, 1, 113. I can't subtract 170 again, right? So then what would I do? Yeah, so we were going to do the 17 times 1s, and we'll subtract 17 each time now, for as many times as it takes. So this would give me 66? Yes? That's not right. 96? I was like, that's not right. I was subtracting a 5 in my mind. 96? Cool. 17 again. 79. Hope y'all are checking me because I'm doing just this really fast. Is that all right? Yeah? Okay, good. 17 again. 62. Okay, we'll keep going. 62 minus 17. $45. Again. And I think this will be our last time. Okay, so we have a remainder of 11 here at the end. but how many times did it go in? All these. So I have 10, 20, 30. 1, 2, 3, 4, 5, 6. It's 36. Remainder 11. Okay, so is it longer? I mean, there's more steps written out, but if you would see the scratch work that my children do to try to do long division when they don't know what the divisor is doing like this, I don't know that it takes them any longer than it would take them if I taught them how to do this. I don't know that it does. So this is another method, partial quotients. All right, so we're going to take a look at some word problems now that incorporate some of the things that we've done in this section with division and some multiplications and some other things too. So we have Juan. Juan saved $53.40 in 3 years. If he saved $95 per month the first year, and then a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? Okay, does everybody have an understanding of what's going on? Okay, so for the first year, he's sticking in there like 95, 95, 95 every month for a year. And then he changes after 1 year and he's putting something else in. And we're trying to find out what that something else monthly is after the first year. So thinking through his situation, what would I need to do first? Okay, and why would I want to do that, Gracie?
To get out of the way that first year.
Okay, so we want to know how much did he save the first year. That sounds like a good plan. So our first thing we're going to do is 95 times 12. And I'm going to do this, I'm going to try to do some of these anyway with alternate algorithms just to remind you, since we've kind of mushed them all together now here toward the end with these kind of word problems. We're going to do it with lattice. Not because we have to, but just for practice and doing one of the other methods. So if you'll remember, the lattice method looks like creating a box where we have, it's a 2 by 2 box because I'm multiplying 2 digits by 2 digits. I put the numbers as they are on the top and on the side, and I split along diagonals each of my boxes, like so. And then I multiply in whatever order, really, among each of my boxes. So I'm just going to start from the top and go down. So the top left is going to be 9 times 1 is 9, and then 5 times 1 is 5. On the bottom left, I have 9 times 2, which would be 18. On the bottom right, I have 5 times 2, which would be 10. Okay, does everybody remember the lattice method? We did it a couple class periods ago. We extend each of these diagonals out, and we start with the bottom corner. It's a 0, bottom right-hand corner, it's a 0. And then we move up along diagonals. So I have 8 plus 1 plus 5, which is 14. So I write down my 4 and I carry my 1. I have 1 plus 9 plus 1, which is 11. So I would write down the 1 for the 11 and carry a 1. I don't have anything in that top box, so there's a 1 out here. So during the first 12 months, the first year, actually I'm going to write it like this. This is year 1. During year 1, he saved $1,140. So what am I going to do with that $1,140 now? I don't think so. Okay, so if he did that for 2 years, we could double it, and that would work great. But he only did it for 1 year. So what am I going to do? Subtract it from the total he has saved, which was $5,340. So we have our $5,340. This is sort of step 2 minus my $1,140. So if you wish, you can write that like this. I'll write it that way instead. And we'll subtract. This subtraction is actually really nice because there's no regrouping needed. So move left to right, move right to left. It doesn't make any difference on this. I have 0, 0, 2, and 4. So I have 4,200. Okay, is everybody good?
Yeah.
Now what?
Divide 2 by 42.
Okay, so I know why you're doing it. Can you tell why you're doing it though, Gracie?
Do you want me to say like why?
Yeah, why would you want to do it that way?
Because now we have 2 years left and $4,200 over those 2 years, and it's a fixed amount, the same amount for
Okay.
both years per month.
Mhm.
So I was just going to divide to get what number he has now in these final 2 years, and then divide that number by 12.
Okay, So your thought was to take the total amount for the 2 years that are left, which is our 4,200, and divide it in half so we can consider just 1 year. Does that make sense? You could divide it by 24, yeah. So there's two different ways to do it, and I think those are both very reasonable ways to do it. So if you want to divide by 2 and then divide by 12, which is a smaller number, so dividing by 12 is definitely easier than dividing by 24 for the same reason that 17 is difficult. 12 is easier. You could do that. If you want, you can just divide by the 24 directly. I'm going to do the 24 directly just because I want you to see what it looks like with that scaffolding, the way that I just did with the partial quotients with it, because it's kind of messy because it takes so many steps on this particular one. So I want you to see that sometimes that the answer ends up taking a really long time with partial quotients, which is definitely a deterrent. I mean, it's a negative for it in certain situations. So if we did it divided by 24, and we have our 4,200, it would be easier if we did it that way. Gracie did actually divide by 2 and then divide by 12. But if we do that this way, then we would subtract 24 times what? 10? That'd be 240. I think we could subtract something bigger. 100? What would that be, Abby? 2,400 instead. Sound good? So we want to subtract the biggest thing we can, because it'll eliminate the need to subtract more times. So 2,400 is a good place to start here. So zeros, 12 minus 4 is 8, so I have 1,800 left. Can I subtract 2,400 again? No. So now I am back to down to subtracting the 24 times 10s. So far I did 100, now I'm at times 10s. And we're going to keep subtracting 240 every time we can until it's too small to subtract from again. So 0, 6, 1560. Another 24 times 10s. 0, 2, 3, 1, so 1320. So 0, 8, 1080. $840. We're getting close. All right, this is my last one. So I have 120 at this point. So this is giving me 10, 20, 30, 40, 50, 60, 70. I think there's 70 of them. Am I done? No. Now what do I have to do? Yeah, so I have to multiply my 24, in this case, by 1. So I'm just going to shift this over. I'm not going to keep writing it underneath because it'll be too small. But I have 120. And we're going to subtract 17 times 1, which is 17. So 120 minus 17. No, sorry, 17 is what I was doing on the last problem. I'm so sorry. 24 is what we wanted. Okay, 24. That's better. It'll take less time. Okay. 96. 72. 48. 24. And then we want to get down to something that is smaller than our divisor. In this case, it happens to divide evenly, so we get to 0. That doesn't always happen, of course. How many times did I subtract my 24? Yeah, 1, 2, 3, 4, 5. There were 70, like there's 7 of these. There's 5 of these, and there's 1 here. There's the 100. So this is $175 per month. Okay, does that make sense? Okay, so as we're doing this, let me just make a statement right here quickly. You don't have to do the scaffolding. You can do your division with your regular division. I don't have a problem with that. There's going to be examples where they're going to tell you what to do. There's going to be examples where you get to pick. So I'm just trying to stick with the ones that are less familiar to you so you can see me use them a few more times, because you're perfectly well aware of how the other algorithm works. All right, let's try another one. We've got Dan. And I know we've actually talked about a question similar to this, or maybe that was my other class. Now I don't know. Maybe it was not this class. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as in the third, and there are twice as many in the second box as the first. How much money does he have in each box? Did we do one in this in your homework like that?
Yes.
It was this class. Okay, good. I couldn't think of which one it was. Good. All right, so when we did this before, we started with a picture. So I think a picture is probably a good way to start. Do you remember some of the methods that you guys looked at or thought about when you were doing this with the 3 boxes before? Nobody? You could change the currency to dollars. That's a possibility. It's probably not going to be any different in terms of how we set it up after that, but it could be possible to help you out into thinking about it. So if I wanted to think about my 4,520 pennies instead of as in dollars, how many dollars is that? Close.
$42.20.
$45.20, yeah. 45.20. So yeah, we can definitely think about it like that. But what can we do in terms of setting up the rest of the problem? Okay, we could do an equation. The other way that you guys saw it last time too, when you were playing with numbers or seeing a problem like this where there was these numbers, is to do trial and error. Because we're dealing with numbers of pennies, I think trial and error might prove tedious. Because while I have $45.20 pennies, I might have something that has 97 pennies. I mean, I don't know that we want to guess and check quite that much. So an equation would probably be a really good idea. And thinking about it in terms of quantities we know and don't know would be helpful. For instance, it says there are 3 times as many pennies in the first box as the third. So whatever's in the third, we'll call it N for the number of pennies, okay? You can do P, you can do X, I don't care. There's 3 times as many in box 1. Does that make sense? Okay, we'll get back to the dollar amounts at the end because giving our answer in dollar amounts I think makes a lot more sense. And then it says there's twice as many in the second box as the first. So what's twice as many as 3N? 6N. Okay, is that good so far? All right, and then it says all these boxes have a total of 4,520 pennies in them, right? So if I combine these all together, 3N plus 6N plus N, I have to equal 4,520 pennies. So what is 3N plus 6N plus N? It's 10N. So what would we need to do in order to divide 4520 by 10? Yep. By 10 by both sides. So what I'm going to show you is a true fact, and I know you know it, but I want to give you a caution in doing it because you need to be very careful that when you do it, you state so specifically to why it's doable. I can cancel the zeros on the end, right? Agreed? That's unique. It's unique to zeros. I had a student go through, it was either this course or proportional and statistical reasoning a number of years back, and I just about died grading the final exam, seeing 9s at the end of things and then just mark 9s out. And this is somebody that's y'all's age. So if someone you guys' age can think that you can just start marking things out, definitely your kids can think that, right? So be careful when you're thinking this that you realize that this is a unique fact to zeros, that I'm able to mark the zeros out. Because what I'm really doing is I'm really taking 4520 and I'm dividing it by 10. Like that's what I'm really doing, right? And I'm saying, well, how many times does 10 go into 45? Well, it goes in 4 times, and that's 40, right? And I have 52. And how many times does 10 go into 52? Well, 5 times, and that's 50. And then I've got this 2 with a 0 coming down. And how many times does 10 go into 20? Well, it goes in 2 times. So we see the 452 coming about right here. And you can see that the elimination of the zeros is appropriate. So I do have 452. So n equals 452. So 452 is right here then, right? So box 3 has 452 pennies. But I don't think that's quite what the question asked for. What did the question ask for? How much money? And you could leave it there, I suppose. It's not technically wrong, but it's a little awkward for exactly the reason I think that Elizabeth said, let's put it in dollars to begin with, right? We don't usually keep 452 pennies in our car. At least I don't, I'll tell you that. So you probably want to change it into $4.52 for it to make it a reasonable amount. Either would be right, but that's probably just a little bit more reasonable. What would we do then to get one of the other boxes? Let's say box 1.
Multiply it by 3.
We're going to multiply 452 in any fashion you wish times the number 3. So I'm going to do that. I'm going to shift these around a little bit. Okay, so we have 452 times 3. And we'll do one of our other methods here just so that we can see it showing up again. So if I do 2 times 3, I get 6. And then if I do 3 times the 5, it's 3 times 50. What's 3 times 50? Like this is 3 times 2. 3 times 50 is actually 150, right? Like that. Because the 5's in the 50 spot. And then I have 3 times 400. This is partial products is the method I'm using. So what's 3 times 400? 1,200. And then we would add them. Again, you don't have to use this method, but we're just going to play with some of the methods. This is 5, 3, 1. So for my box 1, I have 1,356 pennies, or we can think of that as $13.56. What would I do to get the last box, box 2? Yeah, I could take the last one times 2, right? Box 2. So I can take my 1356 and multiply by 2. I'll just use the standard algorithm for this one. So 2 times 6 would be 12. So I put the 2 down and I carry the 1. 2 times 5 is 10 plus 1 would be 11. So I write the 1 down, carry the 1. 2 times 3 is, plus 1 is, and then I've got 2 times 1, so 2. So box 2 has 27, what was it, 12? 12 pennies. And again, if you wanted to put that into a dollar amount, that'd be $27.12. So as you're working on these word problems, whatever method you choose to do, you're going to show the method. All right? You're not going to, I mean, you can grab your calculator to check, of course, that's fine. But you're actually going to show the workout like you would expect your 3rd grader, or 4th grader, or 5th grader to do if they were doing a multiplication or division problem. Sound good? Okay, it's not a whole ton of them you're going to do that on, because you're going to do it for a few of them. All right, the last thing we're looking at in this section is mental math. So there's 2 types of mental math we've talked about before. There's one mental math that just says mental math, and it means we're finding the exact answer. The other type that we do actually says the word estimation, in which case we're actually approximating something. So the first method, that I'm looking at is one of the methods for mental math. And that means we're finding the exact answer. And this one actually talks about breaking up the dividend. So again, strategies only work when numbers are nice to do so. So it doesn't always work, and I get that. But when it works great. So what we do is we take this 6318 and we break it apart. And we break it apart into 6,318. So why would we like to do that? Why is that nice? Grace? Yeah, you can see that 63, hopefully, and 18 are both multiples of 9. That's why it's nice. So as we're thinking about this in terms of writing it out, we can actually write it with the same divisions that we've seen before, like so. I can do the 9 into the 63, or 6,300 as it's written, and that will go in 7 times. And that's 700 because it's going to 6,300. So this is 6,300, right? And then how many times will the 9 go into 18? 2. So as we're sort of thinking about it, what would we be showing work-wise? Well, you probably would show about that much right there. That you've got 6,300 plus your 18, 700 plus 2, this is 702. So you've broken it apart. You've done these 2 little division pieces, right, because they're nice and easy to do in your head. And then you've combined the answer back together. Now, it doesn't always work that it breaks apart quite like this. For example, the next one, I can't really just break apart individuals. Like I see the individual numbers here, right? There's a 63 and there's an 18. I can't do that here. I can't do 42 and 5. 42 doesn't work that way. I can't do 4 and 25 because it doesn't work that way either. But it's close. What you can do is you can recognize that that 4 is not really 4. That 4 is the number 400. So if I were to break this one apart into 400 and the 25 next to it, can 5 go into 400 nicely? Well, yeah, because 5 goes into the 40 nicely. Even though we didn't see the 40 and the 425, it's there, right? Because it's a place value issue. So how many times would 5 go into 40? 8. And so 5 goes into 400 then 80 times. And how many times would 5 go into 25? 5. So we end up with 85. Okay, so that's mental math, finding things exactly. We're breaking up the dividend, the number we're dividing into something else. And then the last one is an estimation technique. So a lot of times estimation techniques take things and they round them or they zero things out. Those are some of the common things we do, right? We round things to nice values and we zero them out. So this one is called compatible numbers. So what compatible numbers is that notice that we would say over here that 6318 divided by 9 were compatible numbers because 63 and 18 were in the multiplication tables of 9s. They're compatible. So as we're thinking about that, what we want to do is we want to look at the 4,132 and think about a nearby value that's easily divisible by 4. What do you think? 4,000 would be pretty good, wouldn't it? Yeah, so 4,000 is easily divisible by 4. So again, we're approximating because it says this is estimation here. So we're approximating, we're changing it to be a compatible number, something that is easily divisible by 4. Is that the only thing you can change it to? No, but it's probably the easiest thing you can change it to, and it's pretty close, right? 4,000 is pretty close to 4,132. And of course, your answer would be 1,000. Any questions on that?
Could you break that up into like breaking up the dividend and do like 40 and 32?
You could change it like that. That would be acceptable. So 40 and 32 would be a compatible number. Yeah, exactly. So the 4,000 part and the 40 at the beginning and then 32 at the end. You could. Yeah. So that's why I said like it's not the only thing that would work. It's just the fastest and simplest, but that would be perfectly reasonable. Okay, let's do group work for this section then.